Look at this modern computer lab. Every one of these network-connected terminals operates in the baseline environment that modern educational technology is designed for: high-speed, well-resourced urban districts. Now, contrast that urban baseline with this photograph of a rural landscape. That single satellite dish mounted on the roof represents the extreme edge of the network, relying entirely on intermittent connections to access the outside world. Here, we see physical bundles of underground fiber optic cables being installed. These lines provide urban schools with rock-solid stability and raw bandwidth exceeding 1 gigabit per second. The rural satellite node operates under severe physical constraints. It averages speeds of around 5 megabits per second, plagued by high latency and frequent dropped packets. This gap in infrastructure creates a specific engineering conflict for EdTech architects. Our mandate at Eduminium is to deliver an identical, synchronous educational experience to both ends of this physical spectrum simultaneously. Addressing this hardware disparity requires a software-first approach. Traditional platforms fail here because their monolithic architectures aren't built to handle these network extremes natively. Here, a traditional monolithic backend attempts to push a massive data block to a client. Hitting a high latency barrier, the packets shatter, crashing the application. The standard response is fallback infrastructure. Teams build separate light codebases or duplicate cloud servers, splitting the system in two. Maintaining bifurcated infrastructure means engineers spend their time patching redundant bugs instead of building features. The technical debt accrues until the system becomes unmanageable. At Eduminium, we set a strict engineering constraint for Project Zero Divide: zero code-based bifurcation and zero infrastructure duplication. We built what we call a dual-track pipeline. It relies on strict end-to-end type safety from the database to the client, paired with semantic AI processing at the absolute edge of the network. Project Zero Divide resolves network asymmetry directly at the architectural level, keeping a single, unified codebase intact. To understand how this works, we have to rebuild the data pipeline. It starts here, with the foundation. Network loads fluctuate based on schedules. We utilize TiDB MySQL Serverless because it scales instantly on demand, absorbing spikes without manual provisioning. Above the database, we lock in Drizzle ORM as our translation layer. Drizzle enforces strict structural typing. It takes raw SQL schemas and turns them directly into TypeScript objects with zero runtime overhead. The data structure is locked in place before it ever moves. Look at this group gathered around a single screen. In resource-constrained environments, backend data integrity directly determines whether a lesson loads on that specific laptop. But database scaling and strict typing solve nothing if the data payload is bloated before traveling across an unstable network. This diagram shows our rejection of traditional REST APIs. We route typed data through tRPC 11, creating a direct transport layer to the React 19 frontend. This guarantees end-to-end type safety. Client and server share exact structural expectations, natively preventing data mismatch errors. tRPC reduces the payload size by stripping out the metadata and scaffolding that standard REST APIs force through the network. Total data integrity is verified internally, ensuring the structure is optimized before a single byte touches the external network. On the receiving end, the React 19 frontend utilizes server components to ingest these minimized payloads, rendering the user interface with high efficiency. tRPC creates an incredibly lean pipeline, but it cannot override physics. It cannot alter the raw byte weight of heavy multimedia lessons heading toward a 5 megabit bottleneck. This is the exact point of system stress. Data flows smoothly to the urban fiber node, but the high latency Starlink boundary triggers an immediate alert. Our pipeline detects these critical latency spikes, instantly halting the flow of heavy packets. When the threshold is breached, the system deploys an instance of Gemini 1.5 Flash, spinning it up as dynamic middleware exactly where the blockage occurs. The large language model intercepts the heavy, media-rich educational payload before it tries to cross the satellite connection. It performs active semantic compression. The AI extracts the instructional core, restructuring it into minimal text data without losing the lesson's context. A dense, multi-megabyte payload is processed into a few kilobytes of highly concentrated semantic data. The React 19 client safely receives this lightweight payload. It then accurately rehydrates the educational interface locally, bypassing the limitations of the 5 megabit connection. Utilizing Edge LLMs as active network middleware allows us to mitigate the impact of limited bandwidth. It ensures functional parity across the network without requiring separate codebases. Here is the fully assembled dual-track pipeline. It routes asynchronous data logic to both network extremes simultaneously. This routing is completely invisible to the students and teachers using the platform, and it requires zero manual branching by the engineering team. But institutional deployment requires one final piece of infrastructure: absolute distributed security. We integrate supertokens to manage distributed session states, enforcing corporate-grade compliance and authentication across every layer of the pipeline. Architectural speed and AI compression matter only if the underlying framework possesses the security rigor demanded by state-level procurement offices. Eduminium has engineered a unified tech stack capable of maintaining high-fidelity educational delivery, regardless of a school's geographic location or network quality. For GovTech officers, software architects, and technical VCs, this architecture eliminates the technical debt of light app maintenance permanently. Do not route through standard subscription channels or consumer-facing trials. Send an email directly to ventus@eduminium.io to schedule a custom technical deployment demonstration with our engineering team today. Educational access is built in the pipeline. It requires engineering scalable parity for every node on the map. We'll see you in the next deployment.